Hello, this video is in response to an email I received asking how Wumpus Mazes work. So I've cloned the original TI-90, 99 game for the NES and the color computer, but I didn't do like a reverse engineering. I just stared at the thing until I could kind of figure out how it worked. So that's what I'm going to talk about here is like how do we generate something that looks like this with all the twisty little passages. So if you stare at this long enough, you will see that there's 5 different types of rooms or locations. So you're going to need some tiles, some graphic tiles to represent those tunnels. And then you're going to need some constants to describe, to indicate which type of location a particular room is. You're also going to need some sort of class, structure, object that defines what's in a room. So the way I did it, a room knows where it is on the screen, like what kind of box it is on the screen, and then it's got an indicator for its type and an array of its neighbors. And if you're actually making a real Wumpus game, you're going to need booleans or bit flags to indicate what's in those rooms. So, and then you're going to want an array or a list of those. So what I did was I used an array because I was in assembly language. If you're in a more modern language, obviously like a list is probably the way to go. So I reserved for space for more mazes than for more rooms than we're actually going to see on the screen. So in this example, I'm going to talk about a 6x8 or 8x6 maze. So that'd be 48 rooms. But I'm going to allocate 64 rooms because when we start adding tunnels, we're going to use up those extra rooms. So just to recap, we're going to start with the number of rooms that we see on the screen, and we're going to either reserve space for more rooms or have the ability to add them on the fly, like using a list. Because what's going to happen is we're going to take a room and we're going to take that first room, or the room that we pick, and we're going to turn it into one type of tunnel, and then we're going to add another room that's the adjoining type of tunnel. So every time we take a room and we convert it into a tunnel, we're adding an extra room onto the maze. And that room is going to get its neighbors from the original room, and it's going to have the same screen coordinate that room will have the same coordinate on the screen as well. So now here's the process for creating a tunnel. Just pick a room that's not a tunnel and change its type to be one of these two things. Well, so there's two ways to do this, and I'm going to show both. So we're going to take like a room, and we're going to say you're tunnel 1 now. You're one of these curvy guys, and then we're going to allocate a new room or grab one of our rooms from our array that hasn't been used yet, and we're going to turn it into the matching type of tunnel. And then we're going to set in this example, we'll set the up and right neighbors of the new room to be the up and right neighbors of the original room. And then we're going to disconnect the original room that we grabbed from the maze. So we're going to set its up neighbor and its right neighbor to -1, so you can't go that way. So we're going to make a new room, hook it into the old room's neighbors, and then disconnect the old room's neighbors where you wouldn't be able to go anymore. All right, and I can see my slides have already gotten out of order. It's a very small presentation, but here, we're going to start out with an array of rooms, a grid of rooms like this, and then we're going to just, depending on the skill level that you want, we're just going to repetitively or iteratively perform this room adding algorithm. So, and it's going to take one of two forms. It's going to be the one that I just talked about. We take a room and we convert it into this tunnel and add this type of tunnel to the game, or we're going to do sort of the opposite of that. We'll take a room, convert it to be a tunnel 3, and then allocate a new room, make it the matching type of tunnel, set its up and left neighbors to be the up and left neighbors of the original room, and then we'll disconnect the original room's up and left neighbors because you can't go that way anymore. Now, one cool quirk of this algorithm is that it is possible that the repetitions will generate a closed loop, and I've seen this in the original game a couple of times. They even had one game where there were two completely closed circles. And that can be a problem because if a bat drops you off there or you start there, you can't get to the rest of the world. It does not happen very often, but you could check for that case. You could generate a maze, and then for every tunnel, just make sure you can get to a room. Do a BFS or something like that, or a DFS. Now, for marking the hazards in the room, we're going to use a breadth first search algorithm. So just pick a room, put the Wumpus in it, mark that there's a Wumpus there, and then find the neighbors of that room and mark them as having slime. So you're going to need a function called like find end or something, that you give it a room and a direction, and it crawls down through the tunnels until it hits a room, and then you can mark that. And as you do that, put those room numbers into a list, and then perform the same operation on those. Pull those rooms out, go to each one of those, the neighbors of those rooms, and mark them. And now you've marked every room that's 2 away from the Wumpus. So that's what I did. I didn't reverse engineer the original code. I just stared at it over and over again until I was like, oh, okay, I think I have a rough idea how this works. And when I do mine, like, I get the closed loops the same way the original one does. So there you go. I hope you find that useful, and happy Wumpus hunting.